Chapter 9, Section 2. Something that we would like to be able to do with two variables is talk about what their graphs look like. As you can imagine, it's much harder to visualize a graph with two variables than if you had one single variable, which we're accustomed to. So in order to visualize a function of two variables graphically, we draw a surface in space that we call a contour diagram. Here's an example of a contour diagram that's typical of things like weather. Now here we have temperature is a function of x and y, which gives the predicted high temperature as a function of x, the latitude, and y, the longitude. So here you can see that we have these lines, which we call contour lines, that help predict the weather. So for example, the predicted high for Topeka, which is here, is going to be in the 80s. Now, most of the stuff we do is not going to be topological. Most of it will be more functional and mathematical. So let's look at some examples of how we can read these graphs, how we can draw these graphs, and how we can interpret different things about these graphs. Okay, so the most practical application is starting with a contour diagram and finding out information about the function from it. So we want to use the contour diagram below to find the following values for f, which is a function of x, y. Again, the order is going to be important to help us read off these values. So for part A, we want to find f of 20, 10. Remember, 20 is the x value, 10 is the y value. So what we want to do is we want to go to x equals 20, we want to go to y equals 10, which is here, and see where they intersect, which is this point right here. As you can see, one of our contour lines goes right through that point, and the value of that contour line represents the value of capital F. So at f of 20, 10, the value is 8. So whenever you land right on the contour line, you have an exact value. Now, for part B, we're looking for f of 20, 5. So again, we go to 20 for x and 5 for y. Notice now that we're not on one of these nice blue lines. Instead, we're sort of in the middle. So what we want to do is we want to estimate where we are between these contour lines. If we go up 5 units, we're at 8. If we go down 5 units, we're on the 6th line. So we're about halfway between the 8 and the 6. So that tells us that we're going to be right about 7. So we're going to estimate to be between these two lines. Now, the other thing we can look at is if we have a value for the function, capital F, and then either the x or the y value, we can find the other one. So for part C, we have if capital F equals 6, that means we're somewhere along on this 6 contour line, and x equals 10, so we want to see where this contour line intersects with x equal to 10, then what is y? Well, here, the 6 intersects right here, so we're looking for the y value. So notice if we come over here, our best estimate is going to be right about 7. Okay, it's a little bit less than half. So we're right in between 5 and 10, a little bit less than half, so I would say the y value is 7. So again, if you're given the capital F value, or the function value, that means you're on this contour line somewhere. So that's how we read these values right off of a diagram. The next thing we want to talk about is looking at one of these graphs and determining if the function is an increasing or decreasing function of its variables. We did this with a table, so now we want to be able to do this with a graph. So for part A, we're going to look at whether or not our function is an increasing or decreasing function of x, and for part B, we'll look at whether it's an increasing or decreasing function of y. So for part A, if we're trying to determine if it's an increasing or decreasing function of x, what that means is we want to know what's happening to the function values as x increases. So that means we're going to pick a value of y to fix. So let's just pick 3. So here we're going to move along the x-axis and see what happens to our f values. So at 3, the first f value that we hit is this line that's 8, the 8 line. As we move, as x increases, we then hit 14, we then hit 20, and then we'll hit 26 if that line was extended. So what you can see is as we increase the x values, as long as y is fixed, these values of f are increasing. So that means our function is an increasing function in x. Now what about the y's? So the same idea, we want to see what happens to the f values as y increases. So that means we're going up and down, right, for y. So we want to pick a value of x, and we want to fix it, and we want to see what happens to the values. So if we take x equals 1, and we move upwards as y increases, we have 32, then we hit the 26 line, then we hit the 20, then we hit the 14, then we hit the 8. So what we see here is that our f values are decreasing as y is increasing. So our function is a decreasing function in y. Here, that's how you're going to interpret if functions are increasing and decreasing. This will become important later when we calculate something called partial derivatives. What about looking at contour diagrams algebraically? What if we start with a function and we want to find and draw a contour diagram to represent that function? So suppose that r, which is revenue, equals 350x plus 200y. And we want to draw a contour diagram for the following values of r: 4,000, 8,000, 12,000, 16,000. How do we set up our contour diagram? So what we want to do is we want to take our original function and set it equal to each of the values of r that we want. So 4,000 equals 350x plus 200y, 8,000 equals 350x plus 200y, 12,000 equals 350x plus 200y, and 16,000 equals 350x plus 200y. And then what we want to do is we want to solve each of these equations for y. Fortunately here, each of these will be linear. So I've solved them here. So again, I'm just subtracting the x term over to the left, and then dividing by 200, and simplifying. So for each one, we end up with a linear equation. They all have the same slope in this particular case, but they have different intercepts. So here, when we plot each line, that's how we represent our contour diagram. So for example, let's look at the fourth equation. We have 16,000 equals 350x plus 200y. Solving for y gives us y equals negative 7/4 x plus 80. So when x equals 0, y equals 80. We have a slope of negative 7/4 x, and eventually it's going to cross the x-axis between 40 and 50. So we take that particular line and we label it with our value of r, what we've set it equal to. And we graph these all on the same axis to represent this contour diagram. Now usually when you're going to have to draw this, it's going to be linear. However, you could also end up with something that would be quadratic, which would look like a parabola, or other types of shapes that you can graph on your calculator. Alright, so the last thing we want to do, which is related, is sketch a contour diagram based on a table. So here, we have a very basic table where our x values are 1 and 2, and our y values are also 1 and 2. And we have our function capital F, which is a function of x and y. So the first thing we want to do is try to figure out an equation that governs our function. We did something similar to this in the last section. So here, if we want to try to figure out the slope, or what's going on, we want to look at the change in the function over the change in the variable. So let's start with the x's. So our x's, if we look at the change of the function capital F over change in x, we have 5 minus 0 over 2 minus 1. That gives me positive 5. If I look at the change in f in this row, I have 0 minus negative 5, which is 5, over 2 minus 1, which is also 5. So the change in x is going to be 5, so I represent that by 5x. Now I also want to see how the change in y is related to the function. So what I want to do is the change in the function over change in y. 5 minus 0 divided by 2 minus 1 is going to give me a slope of negative 5. And if I do this column, 0 minus 5 is negative 5, divided by 2 minus 1 is also negative 5. So I have a slope of negative 5y here. it's always a good idea to plug in a couple values and make sure you're getting the right answer. So here, if I plug in 2, 2, I get 10 minus 10, which is 0. That checks out, and all the others check out as well. So now that we have the table set to an equation, we can do what we did in the last problem. So what we want to do is we want to take our equation and we want to set it equal to each of the functional values. So that's -5, 0, and 5. So if we set 0 equal to 5x minus 5y, -5 equal to 5x minus 5y, and 5 equals 5x minus 5y, again we can solve each of these equations for y and plot them simultaneously. So here the first one turns into y equals x once we simplify it, which is graphed in blue. The second equation turns into y equals x plus 1, which is graphed in red, and the green is y equals x minus 1. So now we have a nice contour diagram representing this table here.